To determine the appropriate wire size, we'll use a formula that takes into account the total current, the wire's ampacity, and any necessary correction factors. The wire size in American wire gauge, or AUG, can be calculated using the following formula: AWG equals log of current divided by ampacity correction factor, divided by log of 2. Let's break down each component of this formula. The current is the total current flowing through the wire, measured in amps. Ampacity refers to the current carrying capacity of the wire, and this is based on the wire material, insulation type, and the operating temperature. Correction factor is a factor used to adjust for temperature, dearthing, and parallel runs, if applicable. To determine the appropriate size of the overcurrent device, we use a different formula. Overcurrent device size equals current multiplied by a safety factor. Again, current is the total current flowing through the device, measured in amps. The safety factor is a factor to provide additional protection against overloads and short circuits. A typical value for the safety factor is 1.25. Now, let's apply these formulas to a specific example: a 64 kV amps piece of machinery operating at 460 volts, 3-phase. Firstly, we need to calculate the total current. The formula for this is total current equals power divided by 1.732 multiplied by voltage. Plugging in the values, we get total current equals 64 kV amps divided by 1.732 multiplied by 460 volts, which equals 85.9 amps. Secondly, let's calculate the appropriate wire size. Assuming we are using THHN copper wire with a 90 degrees Celsius rating, which has an ampacity of 75 amps, we can plug the values into our wire size formula. AWG equals log of 85.9 amps divided by 75 amps multiplied by 1 divided by log of 2. This gives us an approximate wire size of 2/0 American wire gauge. Thirdly, let's calculate the overcurrent device size. Using a safety factor of 1.25, we get overcurrent device size equals 85.9 amps multiplied by 1.25, which equals 107.4 amps. Therefore, the recommended wire size for this application is 2/0 American wire gauge, and the overcurrent device size should be approximately 107.4 amps. Keep in mind that this is just an example, and the specific values may vary depending on the particular application and local electrical codes. It's always important to consult with a qualified electrician to ensure that the electrical system is properly designed and installed. Additional considerations may include voltage drop, conduit fill, and specific requirements outlined in the National Electrical Code, or NEC. For instance, NEC Table 310.15b16 provides ampacity correction factors for high ambient temperatures. NEC Table 310.15b3 covers adjustment factors for more than 3 current carrying conductors in a raceway or cable. Voltage drop calculations are crucial for ensuring that the voltage at the equipment remains within acceptable limits. A common rule of thumb is to limit voltage drop to 3% for feeders and 5% overall. Conduit fill refers to the percentage of the conduit's cross-sectional area that is occupied by conductors. The NEC specifies maximum fill percentages to prevent overheating and ensure ease of installation. Short circuit current rating, or SCCR, is also an important factor to consider for overcurrent devices and other electrical equipment. The SCCR indicates the maximum short circuit current that a component can safely withstand. It's crucial to select components with an SCCR that meets or exceeds the available fault current at the installation location. Grounding and bonding are essential for electrical safety. Grounding provides a lower impedance path for fault current to return to the source, while bonding ensures that all metallic parts are at the same potential, reducing the risk of electric shock. The NEC provides detailed requirements for grounding and bonding systems. Furthermore, when dealing with motors, the NEC has specific rules for motor circuit conductors, overcurrent protection, and control circuits. These requirements are designed to protect the motor and the electrical system from overloads, short circuits, and other faults. Always refer to the latest edition of the NEC and consult with a qualified electrician to ensure compliance with all applicable codes and standards. Remember that electrical work can be dangerous, and it's essential to take all necessary safety precautions to prevent accidents and injuries. Always de-energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. In conclusion, calculating the appropriate wire size and overcurrent device size is a crucial aspect of electrical system design. By using the formulas and considering all relevant factors, it's possible to ensure a safe and reliable electrical installation. Always consult with a qualified electrician to ensure compliance with all applicable codes and standards. The example calculation assumed THHN copper wire with a 90 degrees Celsius rating and an ampacity of 75 amps. The ampacity of a conductor is affected by its temperature rating. Common insulation types include THHN, THWN, and XHHW. Each insulation type has a different temperature rating, which affects its ampacity. For example, a 12 American wire gauge THHN copper conductor has an ampacity of 30 amps at 90 degrees Celsius, while a 12 American wire gauge THWN copper conductor has an ampacity of 25 amps at 75 degrees Celsius. It is important to select the appropriate insulation type for the application based on the operating temperature and environmental conditions. Ambient temperature also affects the ampacity of a conductor. If the ambient temperature is higher than the conductor's temperature rating, the ampacity must be derated. The NEC provides tables for derating ampacity based on ambient temperature. For example, if a 12 American wire gauge THHN copper conductor is installed in an ambient temperature of 50 degrees Celsius, its ampacity must be derated to 24 amps. The number of current carrying conductors in a raceway or cable also affects the ampacity of the conductors. If there are more than 3 current carrying conductors in a raceway or cable, the ampacity of the conductors must be adjusted. The NEC provides tables for adjusting ampacity based on the number of current carrying conductors. For example, if there are 6 current carrying conductors in a raceway, the ampacity of the conductors must be adjusted to 80% of their rated ampacity. Voltage drop is another important factor to consider when selecting wire size. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. The voltage drop in a conductor can be calculated using the following formula: voltage drop equals to multiplied by K multiplied by I multiplied by D divided by circular mils, where K is the direct current resistance factor for the conductor material, I is the current in amps, D is the one-way distance in feet, and circular mils is the area of the conductor in circular mils. Conduit fill is the percentage of the cross-sectional area of a conduit that is occupied by conductors. The NEC limits the maximum conduit fill to prevent overheating and to ensure that the conductors can be easily pulled into the conduit. The maximum conduit fill depends on the type of conduit and the number of conductors. For example, the maximum conduit fill for 3 or more conductors in electrical metallic tubing, or IMT, is 40%. Short circuit current rating, or SCCR, is the maximum short circuit current that a component can safely withstand without failure. It is important to select components with an SCCR that is equal to or greater than the available fault current at the installation location. The available fault current is the amount of current that would flow in a short circuit. The available fault current can be calculated using various methods, such as the point-to-point calculation. Grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, which helps to trip the overcurrent protective device and de-energize the circuit. Bonding ensures that all metallic parts are at the same potential, which reduces the risk of electric shock. The NEC provides detailed requirements for grounding and bonding systems. Motor circuits have specific requirements in the NEC. These requirements cover motor circuit conductors, overcurrent protection, and control circuits. The purpose of these requirements is to protect the motor and the electrical system from overloads, short circuits, and other faults. The motor circuit conductors must be sized to carry the motor's full load current. The overcurrent protection must be sized to protect the motor from overloads and short circuits. The control circuits must be designed to prevent accidental starting of the motor. Always consult the latest edition of the NEC and consult with a qualified electrician to ensure compliance with all applicable codes and standards. Electrical work can be dangerous, and it is essential to take all necessary safety precautions to prevent accidents and injuries. Always to energize circuits before working on them, and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. The initial calculation provided a wire size of 2/0 American wire gauge and an overcurrent device size of 107.4 amps. However, it is important to verify these values against the NEC and consider other factors such as voltage drop and ambient temperature. Firstly, let's verify the wire size against NEC Table 310.15b16, which provides ampacities for insulated conductors rated up to 600 volts. For a 2/0 American wire gauge copper conductor with THHN insulation rated at 90 degrees Celsius, the ampacity is 175 amps. Since the calculated current is 85.9 amps, a 2/0 American wire gauge conductor appears to be adequately sized based on ampacity. Secondly, let's consider the overcurrent protection. The calculated overcurrent device size was 107.4 amps. According to NEC section 240.4b, if the calculated overcurrent protection size does not correspond to a standard size, the next higher standard size may be used, provided that it does not exceed 800 amps. Therefore, the next higher standard overcurrent device size would be 110 amps. However, it's important to verify that this size does not exceed the maximum overcurrent protection allowed for the motor. NEC section 430 provides rules for motor circuit protection. The maximum overcurrent protection for a motor depends on the motor's full load current and the type of motor. Assuming this is a standard motor, the maximum overcurrent protection is typically 250% of the motor's full load current. In this case, the motor's full load current is 85.9 amps, so the maximum overcurrent protection would be 214.75 amps. Therefore, a 110 amp overcurrent device would be acceptable. Thirdly, let's consider voltage drop. As mentioned earlier, the NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. To calculate voltage drop, we need to know the length of the conductor. Assuming the length of the conductor is 100 feet, we can use the voltage drop formula to calculate the voltage drop. Voltage drop equals 2 multiplied by K multiplied by I multiplied by D divided by circular mils. For copper conductors, K is approximately 12.9 ohms circular mils per foot. The current, I, is 85.9 amps, and the one-way distance, D, is 100 feet. The circular mils for a 2/0 American wire gauge conductor is 133,100. Plugging these values into the formula, we get voltage drop equals 2 multiplied by 12.9 multiplied by 85.9 multiplied by 100 divided by 133,100, which equals 1.67 volts. The percentage voltage drop is calculated as voltage drop divided by voltage multiplied by 100. In this case, the percentage voltage drop is 1.67 volts divided by 460 volts multiplied by 100, which equals 0.36%. This is well below the NEC recommended limit of 3% for feeders, so voltage drop is not a concern in this case. Fourthly, let's consider ambient temperature. If the ambient temperature is higher than the conductor's temperature rating, the ampacity must be derated. The NEC provides tables for derating ampacity based on ambient temperature. Assuming the ambient temperature is 30 degrees Celsius, which is within the conductor's temperature rating, no derating is required. Fifthly, let's consider conduit fill. The NEC limits the maximum conduit fill to prevent overheating and to ensure that the conductors can be easily pulled into the conduit. The maximum conduit fill depends on the type of conduit and the number of conductors. Assuming the conductors are installed in electrical metallic tubing, or aimed, the maximum conduit fill for 3 or more conductors is 40%. The area of a 2/0 American wire gauge conductor is approximately 0.373 square inches. Assuming there are 3 2/0 American wire gauge conductors in the conduit, the total area of the conductors is 1.119 square inches. The area of a 1/2 inch EMT conduit is approximately 1.5 square inches. The conduit fill is calculated as the total area of the conductors divided by the area of the conduit multiplied by 100. In this case, the conduit fill is 1.119 square inches divided by 1.5 square inches multiplied by 100, which equals 74.6%. This exceeds the NEC recommended limit of 40%, so a larger conduit size would be required. In summary, based on these calculations and considerations, a 2/0 American wire gauge copper conductor with THHN insulation and a 110 amp overcurrent device would be acceptable for this application, provided that a larger conduit size is used to comply with conduit fill requirements. It is important to consult the latest edition of the NEC and consult with a qualified electrician to ensure compliance with all applicable codes and standards.